Something is wrong with the official story of 3I Atlas. When hundreds of amateur astronomers around the world pointed their telescopes at this interstellar visitor, they all saw the same thing: an object behaving in ways that shouldn't be possible. The coma twisted and morphed night after night. The brightness pulsed like a heartbeat. The jets fired in directions that defied every model we had. For weeks, the raw data piling up from backyard observatories told the story of something genuinely strange crossing our solar system. Then NASA released their official images, and suddenly, 3I Atlas looked completely normal, calm, stable, almost boring. The same object, two completely different stories, and the question that no one at NASA wanted to answer was simple: which version is real? This isn't about conspiracy. This is about what happens when you compare the raw truth to the processed version. And what that comparison reveals about 3I Atlas might be the most important part of this entire story. Let's start with what amateur astronomers actually saw. Between September and November 2024, over 200 independent observers captured 3I Atlas using everything from high-end observatory equipment to modified DSLR cameras on backyard mounts. And here's what made their data so valuable. It was immediate, unfiltered, and brutally honest. The first thing observers noticed was the coma's behavior. Unlike typical comets that maintain relatively stable outgassing patterns, 3I Atlas showed dramatic asymmetry that changed on timescales as short as 48 hours. Australian observer Terry Lovejoy documented a pronounced northeastern jet on November 3rd that had completely rotated to face southeast by November 5th. That's not normal rotation for an object with an estimated 15-hour spin period. The brightness variations were equally bizarre. Photometric measurements from the AAVSO network showed flux changes of up to 0.4 magnitudes over single observing sessions, far exceeding the expected variability from rotation alone. Some nights, the nucleus appeared distinctly non-stellar, almost elongated. Other nights, it snapped back to a sharp point source. And then there was the color. Multiple observers using RGB filters reported that 3I Atlas showed an unusually neutral color profile, almost gray, when most active comets display obvious green or cyan tints from cyanogen and diatomic carbon emissions. The spectra didn't match expectations. The morphology kept shifting, and the object's behavior pattern suggested something was affecting its outgassing in ways we don't typically see with solar system comets. This raw observational data painted a picture of an active, variable, possibly tumbling object with unusual composition or structure. Then, NASA dropped their images, captured using the Hubble Space Telescope's Wide Field Camera 3 on November 8th. These weren't just better quality versions of what amateurs saw. They were fundamentally different presentations of the same target. The official NASA image showed a symmetric, well-behaved cometary coma with a smooth brightness gradient. The jets appeared organized and consistent. The nucleus sat centered in a nearly circular cloud of material. The color was normalized. The texture was uniform. It looked exactly like what you'd expect from a professional space agency: clean, scientific, publishable. But here's where image processing becomes crucial. NASA's pipeline for Hubble data involves multiple stages that fundamentally transform raw photons into the images you see in press releases. They start with dark frame subtraction to remove sensor noise. They apply flat field corrections to eliminate pixel sensitivity variations. They stack multiple exposures using drizzle algorithms that interpolate between pixels. They apply cosmic ray rejection that can sometimes remove real point sources. They use wavelength calibration that shifts the actual colors captured. And critically, they apply contrast enhancement and dynamic range compression that make faint details visible but can smooth out rapid variations. Each of these steps is scientifically valid and necessary for certain types of analysis. But each step also makes choices about what signal to amplify and what to treat as noise. And when the object itself is behaving strangely, as 3I Atlas clearly was, those choices determine which version of reality makes it into the final image. The result is that NASA's image represents a time-averaged, noise-reduced, contrast-optimized interpretation of 3I Atlas. Meanwhile, amateur images represent higher cadence, minimally processed snapshots that capture the object's actual moment-to-moment behavior. So what are the actual measurable differences? Let's get specific. First, coma morphology. Amateur stacked images from November 7th to 9th consistently show a primary dust tail extending 18 to 22 arc minutes toward position angle 285 degrees, with a secondary fainter feature at PA 310. NASA's November 8th image shows only the primary tail, smooth to appear continuous, with the secondary feature effectively erased below the detection threshold of their processed image. Second, nuclear brightness profile. Amateur point spread function measurements indicate the nucleus has a FWHM of 1.8 to 2.3 arcseconds across different observations, suggesting either real size variations or atmospheric seeing effects. NASA's deconvolved image shows a consistent 1.2 arcsecond nucleus, which represents Hubble's diffraction limit rather than the object's actual apparent size variation. Third, surface brightness distribution. Amateurs measured the coma's surface brightness falling off with an exponent of -1.2 to -1.6, indicating potentially multiple overlapping gas shells or jets. NASA's processed image shows a cleaner -1.4 profile, consistent with a steady-state outgassing model, because their pipeline smoothed the irregularities into an averaged radial profile. Fourth, color information. Amateur RGB photometry showed the coma's BV color index varying between +0.62 and +0.71 across different nights. NASA's calibrated image presents a single BV of +0.68, which is technically accurate as a median, but doesn't capture the variation that amateurs documented. None of this means NASA did anything wrong. Both datasets are scientifically valid. They're just answering different questions. Amateur data captures variability and real-time behavior. Professional observatory data captures high-resolution structure and precise astrometry. The problem only emerges when the public sees both and wonders why they look so different. This comparison matters for 3I Atlas specifically, because this object's nature is still fundamentally uncertain. Is it an active comet? A debris cloud from a disrupted body? Something we haven't categorized yet? The behavior captured in amateur observations, the rapid changes, the asymmetric outgassing, the unusual color, all of that data is crucial for understanding what this visitor actually is. When NASA's pristine image suggests a calm, well-behaved object, but dozens of independent observers documented erratic behavior, we need both perspectives to build an accurate model. The processed image is perfect for measuring precise positions and doing astrometry. The raw captures are essential for understanding the physics of what's happening on and around this object. And this isn't unique to 3I Atlas. This same processing gap affects how we present almost every space phenomenon to the public. Remember Oumuamua? The actual observations showed tumbling, acceleration, and bizarre light curves. But the press images made it look like a stable, well-understood object. Same story with many exoplanet discoveries, where the image you see is actually artistic interpretation of processed spectra. The broader lesson is that space imaging exists on a spectrum between raw truth and processed clarity. Neither end is wrong. Raw data is messy but honest. Processed data is clean but interpreted. Understanding both gives you the complete picture. What does all this actually tell us about 3I Atlas? The fact that it shows such dramatic variability in amateur captures suggests this object is genuinely unusual. The rapid changes in coma morphology could indicate a tumbling nucleus with localized active regions, similar to what we saw with Comet 67P/Churyumov-Gerasimenko. The neutral color and unusual spectra might mean this is an interstellar comet with a very different composition than our solar system's icy bodies, possibly formed in a colder, more distant stellar system. The truth is, we need both types of observations. We need NASA's high-resolution structural data to understand what 3I Atlas is made of. And we need the amateur community's continuous monitoring to understand how it behaves over time. Put them together, and you get a complete picture of a genuinely fascinating interstellar visitor that's teaching us new things about how objects from other stellar systems differ from our own. The images don't contradict each other, they complement each other. And that's the real story. Next time you see a polished space image from NASA or ESA, remember, there's probably a community of amateur astronomers who captured the same target and saw something slightly different. Both versions matter, both tell truth, and understanding the gap between them makes you a smarter observer of the universe. If this breakdown changed how you think about space images, hit that like button and subscribe to keep exploring the real data behind the headlines. The universe is stranger than the press releases suggest, and we're here to show you why.